All right, welcome everyone. Today we're going to continue talking about Taylor and Maclaurin series. So last time we introduced those ideas. We introduced what they were, saw the definitions, saw how to calculate those for a given function. And today we're going to see more examples like that. But first we're going to start with this theorem. And it says if a function has a power series representation centered at A, well then the function is actually equal to its Taylor series centered at A. And that's what this says. It says f of x is equal to its Taylor series. So if we know a function can be represented as a power series, well then f of x has to be equal to its Taylor series for certain x values. So we have this extra condition here. We're guaranteed to have this equality when the absolute value of x minus a is less than the radius of convergence. So this is like this inequality here is really describing the interior of our interval of convergence, everything in between the endpoints. We know the endpoints, there can be potentially issues for our interval of convergence, but inside those endpoints, our function is guaranteed to equal its Taylor series expansion. And that's pretty remarkable. So if our function has a power series representation, well then it has to be this Taylor series. And that's all there is. Now a couple comments. The first comment here is this theorem does require that our function has to have a power series representation. So unfortunately there are functions out there that do not have a power series representation for certain a values, for certain center values. But the second point is we're not going to be looking at those. So we're going to be primarily concerned about functions that do have power series representations. So, there are functions out there that cannot be represented as a power series for certain center a values. But the functions we're going to be looking at and the a values we're going to be considering, our functions are going to have a power series expansion. And if our function has a power series expansion, well, it can't just be any power series. It's going to be equal to, our function is going to be equal to the Taylor series. So let's actually prove this result, or at least sketch out what a proof might look like. So let's start with, let's suppose that our function f has a power series representation centered at A. And what this means is that our function f of x is equal to the sum from n equals 0 to infinity of c sub n times x minus a raised to the power n, where c sub n, these are the coefficients. And in order to prove this theorem, what we need to do is we need to figure out what these coefficients are. So let's start by writing out the first few terms of the power series expansion. So let's start with f of x, and let's write out maybe up to n equals 4. So we'll have c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared plus c sub 3 times x minus a cubed plus c sub 4 times x minus a to the 4th, and it keeps going like that. So we've just written out the first few terms for our power series expansion. And what we want to do is we want to calculate what these coefficients are. So let's plug in our center value a into this power series representation. And when we do that, what's going to happen is c sub 0 is just a constant, so that's we're going to be left with. And then all of the remaining terms here have this x minus a factor. So when we plug a into that, it's just going to be 0. So we're going to end up with c1 times a minus a, which is 0. So this will be 0. And then when we plug a into this, we'll get c2 times a minus a squared. So c2 times 0. So this will be just another copy of 0 here. And then same thing, plus 0, and so on. And so what we end up with when we plug a into the power series expansion, everything ends up canceling off except for that very first term. And so what we end up with, if we kind of turn this around and solve for this unknown coefficient, we get c sub 0 is equal to f of a. And that's the first coefficient of our Taylor series expansion. All right, now let's try differentiating. So let's differentiate function f. So that'll give us f prime. And then let's differentiate this power series expansion. So when we differentiate c0, it's a constant, so that's just going to differentiate to 0. And when we differentiate this term, we're going to end up with just c1. And then when we differentiate with the next term, power rule, so we bring down the 2, put it in front, the coefficient stays the same, subtract, keep the x minus a the same, and then subtract 1. So we're going to end up with 2 times c sub 2 x minus a. Then we go to the next term, power rule again, bring the 3 down, put it in front, and then we subtract 1 in the exponent there to give us x minus a squared. And then same thing over here. We differentiate this, we get 4 times c4 times x minus a cubed, and we could keep doing that. And same trick, now that we have this derivative, let's plug a in. And when I plug it into I'm going to plug a everywhere into this power series representation, and c1 is a constant, so I'm going to get a c1. But then when I plug a in here, I'm going to have a minus a, which is 0. When I plug a in here, I'm going to have a minus a squared, which is 0. And then over here, again, 0. So the only contribution that I'm getting is from that very first term. And then everything else is just 0. And I guess, it keeps going like that. So if we put in what we're finding here, we're finding that c1 is equal to f prime evaluated at a, the first derivative evaluated at a. And if we wanted to really be specific, we could think of it as f prime evaluated at a divided by 1 factorial, because 1 factorial is just 1. Let's now do the second derivative. So we're going to differentiate f prime. So let's differentiate the power series expansion. Derivative of c1 is just a constant, so when we differentiate, we get 0. And then when we differentiate this x minus a term, we're just going to get 1. So we're going to have 2 times c2. And then over here, when we differentiate, we're going to have 3 times 2 times c3 times x minus a raised to the power 1. And then we'll have plus 4 times 3 times c4 times x minus a squared, and so on. And same trick. Now let's plug in a. And so what we're going to get is we're going to have this contribution from the first piece, the 2 times c2. But then whenever we plug a into these terms that have an x minus a factor, we're just going to get 0. So it'll just be plus 0, and so on. It keeps going like that. And so if we solve this equation for C2, we're going to get f double prime divided by 2. And we could really think of that 2 as, we can always multiply by 1. So we can think of this as the second derivative evaluated at a divided by 2 factorial. And just to see kind of what this is going to look like, let's calculate the third derivative. So when we differentiate, the 2 times C2 is a constant, differentiates to 0. When we differentiate the next piece, we're going to have 3 times 2, and then really we can always put a multiplication by 1 in, times C3. And then when we differentiate over here, again, power rule, bring the 2 down, we'll put it next to the 3. So we have plus 4 times 3 times 2 times C4 raised times x minus a, and then this keeps going. And so when we plug a in, this term is just going to end up being 0. And you can see we're going to have 3 factorial times C3. So when we plug in for C3, we're going to end up with our third derivative evaluated at a divided by 3 factorial. And these are just the coefficients that we would expect from our Taylor series. The nth derivative divided by n factorial. And so what happens is, as we keep differentiating, we could calculate more and more of these coefficients. So if our power series, or if our function has a power series representation, can't just be any old power series, it's going to end up being equal to its Taylor series. All right, so this is just to give some idea of, what's happening here, why this, why we're kind of forced into having our function, if it does have a power series representation, why is it equal to its Taylor series? Well, this kind of calculation here. So this is more of a kind of a sketch of what a proof might look like. All right, let's try a few examples though. Let's keep working with Taylor and Maclaurin series. All right, so let's look at example 3. We're going to find the Maclaurin series for the function sine of x. And we know Maclaurin is just a special case of the Taylor series centered at a equals 0. All right, so how to do this is we want to start by just calculating all of the necessary derivatives, and it helps to do, write out the first few terms. So let's do up to the fourth derivative. So we'll start with our function sine of x, and then we'll do the first derivative, which is cosine x. Then we'll do the second derivative, which is negative sine x. Then we'll do the third derivative, which is negative cosine x. And then we'll do the fourth derivative, which is back to sine x. So when you're trying to find, Taylor or Maclaurin series, it helps to write out, ultimately what we're going to do is write out the first few terms, and that'll help us identify the pattern. All right, so to start with this, we want to calculate the necessary derivatives. We have our first derivative, second derivative, third derivative, and fourth derivative. And we know for Maclaurin series, this means a equals 0. So that's what we're going to do, is we're going to plug in a equals 0. So let's plug 0 into our original function. We get sine of 0. Sine of 0 is 0. Now let's plug 0 into our first derivative. So we get cosine of 0, which is 1. Then we do it to our second derivative. We get negative sine of 0, which is still just 0. And then we have our third derivative. We plug it in. We get negative 1. So cosine of 0 is 1. Then we have the negative in front. And then when we plug into our fourth derivative, we get sine of 0, which is 0 again. And then it repeats like this, because at this point we're back to where we started. So we started with sine of x. By the fourth derivative, we're back to sine x. So this pattern is going to repeat. All right. So let's keep that in mind. This pattern is going to repeat. All right. So let's write out the Maclaurin series, the general formula. So our original function, f of x, is going to be equal to f evaluated at our a value, 0, plus the first derivative evaluated at 0 divided by 1 factorial times x, plus the second derivative divided by 2 factorial times x squared, plus the third derivative divided by 3 factorial times x cubed, and then the fourth derivative, which is, well, we'll just write it out, evaluated at 0 divided by 4 factorial times x to the fourth. And it keeps going like this. And if we plug in our values, f of 0 is 0. F prime of 0 is 1. So we're going to end up with an x here. And then the second derivative at 0 is 0. So we're going to have, so the x squared term is going to be gone. So we'll just have a 0 there. And then the x cubed term, the third derivative is negative 1. So we're going to have negative 1 over 3 factorial times x cubed. And then the fourth derivative is back to 0. And you could kind of guess, this starts repeating at n equals 4. So this pattern starts repeating. And so when we have our fifth derivative, what are we going to end up with? Well, we're going to end up with 1 over 5 factorial, x to the fifth, and then plus 0. And then we'll have minus 1 over 7 factorial times x to the 7, and so on. So this first derivative gives us 1. The third derivative gives us negative 1. So here's the negative. And then it's going to repeat. So then the fifth derivative is going to give us positive 1. The seventh derivative is going to give us negative 1. And it keeps going like that. And then all of the even derivatives are going to give us 0. And so we want to write this out. We want to write the kind of the general form for this series. And in sigma notation. And what we notice here is we have all of the odd powers. So if we have odd powers, we can sort of reindex things where we set m equal to our index equal to 2n plus 1. And let's just say 2n plus 1. So that's a way to always guarantee, no matter what n is, this is always going to be odd. We have an even number plus 1, it's always going to be odd. And if we have an even, it would just be 2n. So we have what we have here, writing out the first few terms, we have all of the odd, kind of all of the odd powers. So the way to capture that is we're going to do the sum from n equals 0 to infinity. We're going to have x raised to the 2n plus 1, because that's going to give us 1, 3, 5, 7. It's only going to give us the odd powers. And then, and let's maybe give a little bit more room here. And you know what? Let's So we're going to do the sum from n equals 0 to infinity. And we're going to have the x raised to the 2n plus 1. So that's giving us all of the odd powers of x. And then we want all of the odd factorials. So 3 factorial, 5 factorial, 7 factorial. So same thing. It'll be 2n plus 1 factorial in the denominator. And then if we look, let's write this out without the zeros. So we're going to have x minus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x to the power 5 minus 1 over 7 factorial times x to the power 7, and so on. And what we have here is we've dealt with the odd powers of x. We have our odd factorials taken care of. The only other thing is we have this alternating positive, negative pattern. So how do we get that alternating piece there? Positive, negative. Well, we get -1 raised to the power n. And so that's what we'll put in the numerator here. -1 raised to the power n. And so this is the power series representation, or the Maclaurin series, not for just any old function f of x, for sine of x. So this is the Maclaurin series for sine of x. All right, let's try another one. So let's kind of look at what we did here. So we know for a general function f of x, we could write out the Maclaurin series expansion or the Taylor series expansion centered at a equals 0. And we know that the coefficients all work with the derivatives. So to really get things going, we start with our function and then we just work on a few derivatives just to see what's happening. And why we do this is because we ultimately want to figure out what the pattern is for our coefficients, so we can write this in sigma notation. And so we wrote out the first, up to the fourth derivative here. And as we were doing it, we kind of saw what the pattern was going to be. So it just started repeating at n equals 4. So we were kind of back up to here. And then at n equals 5, we were able to kind of guess, at n equals 7, and so on. And so we wrote out the first few terms, and we had our sigma notation here. Let's try another example. And we're going to repeat this process. So let's do the Taylor series for the function f of x equal to 1 over 1 minus 2x. And we're going to do this centered at a equals -1. All right, so let's start with our process. We want our original function, f of x, and we're going to be differentiating this, so let's use negative exponents. So we'll write this as 1 minus 2x raised to the -1. Let's go through and calculate the first, 4 derivatives. So f prime, what's f prime? Well, power rule, bring down the -1, put it in front, keep what we have inside the parentheses the same, subtract 1 in the exponent, so it takes us down to -2. Now we have some extra stuff here inside the parentheses, so chain rule applies. So we differentiate what's inside the parentheses, we get -2, we multiply that on at the end. So we're doing the general power rule here, or really special case of the chain rule. Then we want the second derivative. So what are we going to do? Let's take this exponent, -2, bring it down, put it in front, just doing some power rule. Keep what we have inside the parentheses the same, subtract 1 in the exponent. We had a -2 there from before, but now we have to do chain rule again, so we're going to end up with another -2 because we're differentiating what's inside again. Let's do the third derivative. Again, we're going to bring down the -3, put it in front, and notice that when I'm doing this, when we're trying to figure out the general pattern, or that's what we're ultimately going to do, it actually helps not to really simplify too much as you do this. So I could be just multiplying these out. I could be doing, oh, this is just 6. And go from there. It actually helps or sometimes it helps, I should say, when you're trying to identify what the pattern is, to not multiply things out. sometimes it's a little bit easier to see what's going on. So that's why I'm not multiplying anything out here. Same thing over here. Could have had a positive 4, just left it as -2 times -2. All right, so we're doing the third derivative. Just a quick note there. So we brought the 3 down, still had the -2 times the -1. Keep what's in the parentheses the same, subtract 1 in the exponent, so that's going to take us down to -4. We still had a -2 times -2 there. And we're doing chain rule again, so now we're going to end up with another -2. And let's do one more derivative. Let's do the fourth derivative. So I'm going to bring down the -4, put it in front. And now at this point, you want to keep in mind what the pattern is going to be. So we have this stays the same, subtract 1 in the exponent, and then we're doing chain rule. So we still have those 3 -2's that we're multiplying, but we're going to end up with another copy now. And when we're doing this, we're going to eventually plug in. So we're going to evaluate this at a equals -1, each of these. And notice that when we have this, this is for n equals 0. This will be for n equals 1, n equals 2, n equals 3, n equals 4. And notice that as we go down the line here, the negatives here are always balanced. So we have this -1. Over here we have a -2. So those negatives are going to cancel. It'll be a double negative. Same thing for n equals 2. It's always going to be balanced on either side here. So we're going to have the -1, the -2. Those are going to cancel, the negatives. Then we have a -2 and a -2. So those are going to cancel. And then same thing. So on the left-hand side here, we keep going down. There's 3 negatives. On the right-hand side, there's 3 negatives. So the negatives are just going to cancel. Same thing for n equals 4. We have 4 negatives over here. We have 4 negatives over here. So all the negatives are going to cancel. So when we plug in, what are we going to get? Let's plug -1 into the original function. We're going to get 3 raised to the -1 power. Let's plug -1 in here into the first derivative. We're going to get 1 times 3 raised to the -2 power times 2. Then when we plug in -1 into our second derivative, we're going to end up with 2 times 1 times 3 raised to the -3 times 2 times 2. And then our third derivative, we're going to end up with 3 times 2 times 1 times 3 raised to the -4 times 2 times 2 times 2. And then finally for our fourth derivative, when we plug -1 in, we're going to end up with 4 times 3 times 2 times 1 times 3 raised to the -5, and then 2 times 2 times 2 times 2. So we're going to end up with, well, you can kind of see what's happening here. So it's kind of fun to do these. And when you don't write out the multiplication, or when you don't calculate the multiplication, when you just write this, notice that what we're seeing here, 3 times 2 times 1, that's 3 factorial. 4 times 3 times 2 times 1, that's 4 factorial. And so if you put all of this together, what we kind of expect is that the nth derivative evaluated at -1, what is it going to be? Well, when n is 4, we have a 4 factorial, so we're going to expect an n factorial. And then when n is 4, we have 2 copies of 2, so we're going to have 2 raised to the n. And that should be a multiplication there, 2 raised to the n. And then we have this 3 raised to the -1. So when n is 0, we have 3 raised to the -1. When n is 1, we have 3 raised to the -2. When n is 2, we have 3 raised to the -3. And when n is 4, if we keep going, we have 3 raised to the -5. So we can really think of this as, instead of 3 raised to the negative 5, we can think of that as 1 over 3 raised to the power 5. And so when n is 4, we have a 3 raised to the power 5. So we have one more than n. So it'll be 3 raised to the n plus 1. And you can verify that. When n is 3, we would have 1 over 3 raised to the 4. When n is 2, we have 1 over 3 raised to the power 3. So in general, for the nth derivative evaluated at negative 1, the terms in the beginning here are giving us n factorial. The terms at the end here are giving us powers of 2. So we're going to have 2 raised to the power n times n factorial. And then the number in the middle is 1 over 3 raised to the n plus 1. And so to find the Taylor series for this function, this function is equal to the sum from n equals 0 to infinity of the nth derivative evaluated at negative 1 divided by n factorial times x plus 1 raised to the power n. So again, just remember here, it's x minus a raised to the n. And so a is a negative, so this is going to end up being a double negative, so that's why it ends up being x plus 1. And now we can fill in what we've calculated for the nth derivative. So let's fill it in. So we're going to end up with the sum from n equals 0 to infinity of n factorial times 2 raised to the n divided by 3 raised to the n plus 1. And then we have this 1 over n factorial. So we could just divide that by n factorial. I'll just write it as multiplication by the reciprocal, so 1 over n factorial there. And then we have our x plus 1 to the n. And then the n factorials cancel. And so we end up with then a nice power series representation for this function. So here's the Taylor series for the function 1 over 1 minus 2x. And this is the Taylor series representation that's centered at a equals negative 1. All right. So in practice, we can use Taylor series to approximate, well, we can use Taylor polynomials, what we call Taylor polynomials, to approximate a function. So given a Taylor series, we call each partial sum the Taylor polynomial of degree n, or t sub n for short. So for instance, t sub 1 is just f of a plus the first derivative evaluated at a times x minus a. So it's just the sum of our n equals 0 and our n equals 1 terms. So this is just the Taylor series, the n equals 0 term. This is just the n equals 1 term. We're just adding them together, and that's giving us our Taylor polynomial of degree 1. Our Taylor polynomial of degree 2, we call it t sub 2, is just f of a plus f prime of a times x minus a. So that's just the n equals 1 part, and then we have our n equals 2 part. So the second derivative evaluated at a divided by 2 factorial times x minus a squared. We're just adding these 3 terms together, and that's giving us our Taylor polynomial of degree 2. And then something similar for t3, our third degree Taylor polynomial. So it's just the n equals 0 part, the n equals 1, the n equals 2, and then the n equals 3. So we add everything up until the third derivative term. And so what these Taylor polynomials do is, if our function has a power series representation centered at some a value, which the functions we're going to be looking at do have a power series representation, well, what these Taylor polynomials help us with is they can be used to approximate the value of our function. They can be used to approximate our function. And we've actually seen this very first one before. This is the linear approximation that we looked at way back in Calc 1 with tangent lines. So we called it something different there, but this is just the linear approximation. This is just the tangent line, essentially. So y equals the y coordinate plus the slope evaluated, or times x minus a, where, if we're thinking of tangent lines, what was the slope of the tangent line? Well, it was just the derivative. So we used a tangent line to form our linear approximation, and really the linear approximation is just a kind of a special case of these Taylor polynomials. So that was one of the big ideas from Calc 1, is that the tangent line can be used to approximate a function, and the slope of the tangent line is the derivative. But we can generalize this idea. Instead of talking about just a linear approximation, we can approximate our function with a quadratic, with a parabola. Or we can approximate our function with a cubic, or higher powers if we want. And let's look at this in example 5. Let's approximate the function 1 over 1 minus 2x with a Taylor polynomial of degree 2, centered at a equals -1. And so this is the function we just looked at in example 4. So we found that 1 over 1 minus 2x was equal to the sum from n equals 0 to infinity of 2 raised to the power n divided by 3 raised to the n plus 1 times x plus 1 raised to the power n. So this is what we found for our Taylor series. And so the Taylor polynomial of degree 2 is where we just write out the first few terms of our Taylor series, essentially. So T2 is equal to, what's the n equals 0? We get 1/3. Then when n is 1, we're going to get 2 over 3 squared times x plus 1. And then when n is equal to 2, we're going to get 2 squared over 3 cubed times x plus 1 squared. And so this is the Taylor polynomial for this function. And so what we say is that near x equals -1, so right around that center point, our function 1 over 1 minus 2x is approximately equal to the Taylor polynomial. And we can see that over here. So we have our function graphed. So there's kind of two pieces of it here. There's the piece above the x-axis, and then there's this piece over here. And we're interested in this function centered at -1. So we're really interested in this function right around -1. And that's where we've really focused our attention here. And you can see we've kind of graphed a few different Taylor polynomials. So we have our linear approximation here, T1. And you can see that right around a equals -1, that gives us a pretty good approximation of what our function's doing. So if you zoom in on that point, you can't really tell the difference between the line, the tangent line, and the curve. Well, T2, what we just calculated here, gives us a parabola that approximates our function at that point. And you can see that gives a nice approximation. And if you zoom in, you can't really tell the difference between the parabola and the actual curve. And if you keep going, here's T5, the Taylor polynomial of degree 5. This is even better kind of approximation. It captures more of the behavior here. And so as you look at higher order or higher degree Taylor polynomials, you're going to capture more and more of the behavior for that function f of x. And you can see here for each of these, right around a equals -1, they look pretty similar to the original function. So they're approximating our original function. So this is useful to take a complicated function and represent it with just power functions. We can take this complicated, this has division in it, and we can just really represent it as just a sum of a few different power functions as a polynomial. So this is useful for really taking a complicated function and simplifying it down. All right, so that's what we're going to look at with Taylor and Maclaurin series. In the next lesson, well, we're going to keep working with them just a little bit more. So we're going to have kind of these very common Maclaurin series, and we'll see how to manipulate them to produce Maclaurin series for slightly different functions. So we'll see that next time. So for instance, the one example, we already have our Maclaurin series for sine of x. If we differentiate that, we'll get the Maclaurin series for cosine x. So, and then we'll play similar games for a few other functions. So we'll see that next time. We'll see you then. Bye-bye.